All right, the last video for Unit 1 is looking at chemical equations. I'm just going to quickly review balancing and then I'll review some stoichiometry. So remember that chemical equations and chemical reactions are different from one another. The chemical reaction is the physical rearrangement of the atoms. It's the thing that you see in front of you during a lab, whereas the representation of the reaction on paper is called the equation. So if you, for example, the equation is actually writing out the reactants yielding the products, but if you were to see the thing happening in front of you, that's going to be the reaction. In a chemical reaction, bonds are broken and new ones are formed. Also in a chemical reaction, you need to remember that all the atoms that are present as reactants must also be present as a product. And that is the law of conservation of mass. If that didn't happen, we would be violating that law, which would not be good. And in order to show that we are satisfying that law or not violating that law, that's why we balance equations. A chemical equation is very important because they provide us with two things. They show us the nature of reactants and products, as well as the relative numbers of each. So, for example, the coefficients are what tell us the relative number, and they also tell us the physical states. So that would be the nature. So whether something's a solid, liquid, gas, or aqueous. And so if something's a gas, we represent it by a little g. So for example, if you're dealing with oxygen gas, you might see that. If something is a liquid, you'll see a little L. So for example, if you're using water, and usually it's a script L so that it's not confused with the number 1. Solid is the other option, and so if let's just say we're writing something with silver, that's going to be a solid. And the final physical state that you'll see is AQ, and that stands for aqueous or aqueous, which means that it's dissociated in water. And just a reminder of that vocabulary, if something's dissociated, that means it's an ionic compound that has been broken apart in water, so the ions have been separated. And so if you were using some sort of salt solution, you would see the salt with a little AQ next to it. And the chemical equation also will allow us to figure out the number of molecules or moles or grams, in some cases liters, that you're looking at in a chemical reaction. Just a couple things about balancing. Hopefully you guys know how to balance equations by now. If not, you got some trouble. So when you are looking at any problem, the first thing that you always need to do is make sure the equation is balanced. If it's not, do that first. And so when you are looking at an equation, in order to see if it's balanced, the number of atoms on each side should be equal. So if you have 6 carbons on one side, you should have 6 carbons on the other side. The identities of the substance must never change, and so the example that I often use is if you're combining hydrogen and oxygen to form water. If you look at this and go two hydrogens on the left, 2 on the right, that's good. 2 oxygens on the left, and there's only 1 on the right. So if you think, okay, I'm going to put a little 2 there, that means I have 2 oxygens now. Well, you've now taken water and converted it into hydrogen peroxide, which means you change the identities. So in order to balance that, instead of doing that, we use coefficients, and so now you put a coefficient over here. Generally, unfortunately for those of you who don't like puzzles, balancing can be a little bit of trial and error, and so it can be frustrating at times. My recommendation to make it a little less difficult is to always start with the most complicated thing first and save the elements that appear in multiple reactants and products until last. And so the example that I will use is a combustion reaction. So let's say the combustion of ethane. Now, I would start with the most complicated one first, so I would start with your ethane, and I would leave the oxygen until last because it appears in multiple compounds. And so if I look at this and go, okay, there are 2 carbons on the left, so I'm going to put a 2 on the right. There are 6 hydrogens on the left on the reactant side, so I'm going to put a 3 on the product side to show that I have 6 on the product side. Now look at the oxygens. There's 2 oxygens on the reactant side, and on the product side we have 4 plus 3 is 7. Well, 7's an odd number, because of the O2, you can't have an odd number. And so in order to fix that, we will multiply everything by 2. So that means I'm going to have 2 here. This is going to become a 4. This is going to become a 6. And now we have 8 plus 6. We have 14 oxygens on the product side. And so I'm going to put a 7 on the reactant side. And now it's balanced. And the last thing, stoichiometry, and as I have mentioned in class, I teach stoichiometry through proportions, and you may have learned with dimensional analysis, and if you do, that's fine. I can show you how to do dimensional analysis with anything that we do in class, or if you want to learn proportions, I would be happy to show that to you, but everything that I do in class will be done using proportions, just to stay consistent with what we're teaching in Chem 1 for those of you who are coming from there. So this is the general equation that you're going to have to know that you use pretty much always whenever you do stoichiometry. And we've done this in class when we were doing mole conversions. The thing to remember when you are now looking at chemical equations is that whatever's on the bottom, whether it's 1 mole or formula weight or Avogadro's number, you have to multiply it by the coefficient from the balanced equation. And I'm also going to add one other one here. So if you add liters, 22.4. This only works at STP. So it allows you to figure out how many moles or how many liters of a gas you have at STP. And we'll talk more about gases next unit. Remember, when you're dealing with this one right here, the M is molarity and the V is volume in liters. And again, we'll deal more with molarity in the coming units when we review that. But this is just the general stoichiometry formula, equation, whatever you want to call it. You will do some limiting reactant questions in here. It's also called limiting reagent, same thing. And so just as a reminder that the limiting reactant or the limiting reagent limits the amount of product and the way that it does that is because it runs out. So if I am making grilled cheese sandwiches, once I run out of cheese, I can't make any more grilled cheese sandwiches. So the cheese would be my limiting reactant because it limits the amount of grilled cheese sandwiches I make, assuming it gets used up first. And as a reminder, when you're approaching limiting reactant questions, you need to do the stoichiometry process twice. And then you choose the smaller amount, and that's your limiting reactant. So, let me go back. So the reactant that yields the smaller amount is going to be your limiting reactant. And then the other one's called an excess reactant. And the last thing is just some vocabulary that you need to be aware of. So the theoretical yield is the amount of product that forms when the limiting reactant is completely used up. It's the maximum possible amount of product that can be formed. It is determined through stoichiometry. And the other type of yield is the actual yield. So the actual yield is the amount of product that is actually obtained in an experiment. It's also a measured value, and the only way to find this is through experimentation. And a representation of how well an experiment was conducted is to find the percent yield. So basically it tells you what percentage of the theoretical yield you actually got. And so the equation for percent yield is your actual yield divided by your theoretical yield and then multiplied by 100 because it is a percentage, and the higher the percent yield, the better. If you got 100% yield, that would mean that you did the experiment 100% perfectly and you obtained the maximum possible amount of product, which is pretty unlikely, but obviously, theoretically, it's possible. And the lower your percent yield, the more product you lost. And we'll talk a little bit about this year your percent error, which is kind of the opposite of percent yield. So you want a low percent error and a high percent yield is the ultimate goal. And if you would like to review a little bit more about stoichiometry and the things that I just reviewed in this video, look at these 2 sections in your book, and you will have some problem sets to work on in class using reviewing this information. So that is just a real quick overview of the stoichiometry that you're going to be expected to know for now. Again, I'll add more to it later, but that's the stuff from Chem 1 that I'm going to expect that you know this year for AP.